Hi there. This video is on section 9.3. We're going to be showing you how to solve separable differential equations, and I will indeed explain what we mean by separable differential equations. All right, so a separable differential equation is any differential equation, in other words, any equation that has a derivative in it, where it is algebraically possible to separate the x's on one side and the y's on the other side. So we're going to separate on different sides of the equation the two different variables, x and y, or whatever variables they happen to be using. But I think all the examples in this homework set use x and y. Let me show you a couple examples of this. So I have example A, which is a very simple differential equation that I used in the previous video. So this is y prime is equal to y over 2. Instead of y prime, I'm going to suggest that we write dy dx. It makes it very obvious where the differentials are. Dx is in the bottom, dy is in top. I'm just going to use some basic algebra to simplify this. So I'm going to divide both sides by y, and I'm going to multiply both sides by dx. And now we've put all the y's on one side and all the x's on the other side. So that's just simple multiplication kind of business division to simplify that algebraic equation. Now I'm going to do something else on both sides. And the thing I'm going to be doing on both sides is finding the antiderivative. So step number one is put all the x's on one side, all the y's on the other side. Step number two is to do the antiderivative of both sides. So the antiderivative of the left-hand side, well, that's the antiderivative of 1 over y dy. And the antiderivative of 1 over y is ln of y plus some constant. On the right-hand side, we have basically 1/2. Whether I put the 1/2 inside the integral sign or outside the integral sign doesn't really matter because it's a constant being multiplied. It won't affect antiderivatives or derivatives. The antiderivative of 1/2 is 1/2 x plus c. Now, this is a different c. So maybe I'll call this C1 and C2. They won't necessarily be the same number, but there are some constants on both sides. In fact, I can just combine these C's together. I can subtract C1 on both sides. And so this would be C2 minus C1. So what we typically do is we don't put C's all over the place. It's just not necessary. You're just going to combine together these constants into one big C. So I'll just put one big C, big C right here, big C on the right side. Or you can put it on the left side, doesn't really matter, but just put one constant. You don't have to put lots of them around there. They're just going to combine together anyway. Now, our goal is to solve, and solving a differential equation means finding the function y that makes this differential equation come out to be correct. So we have solved for ln y, so we need to solve for y. Well, I can again do the same thing to both sides. I'm going to exponentiate both sides with a base of e. E to the ln y is just going to be y. And you get c to the 1/2 x plus c. Oh, used to be the e to the 1/2 x plus c. So this is my solution to the differential equation. If I take this exponential equation and I plug it into this differential equation, I take the derivative, it will come out to be exactly y over 2. And certainly it's a good thing to verify that. We did in the last video a way of checking to see if a solution, you basically just plug it in, you take the derivative, you see if you get the same thing as y divided by 2. If you do, you know you have the right answer. For this video, I'm going to be focusing on finding the particular solution if we're given a point. So this we're given y of 0 is equal to 2, which means when x is 0, y is 2. And we're going to find the particular solution for this differential equation. So we know generally all of the solutions look like this. This is the general solution. And then to find the particular solution, oops, let me change the color there. Particular solution, we'd have to know some information of which particular solution we want. So our particular solution is going to be the one that's at 0, comma 2, because it says y of 0 is equal to 2. So I'm just going to plug that in. If we have information, we know x is 0, y is 2. Let's just plug it in. So we get 2 equals e to the 1/2 times x plus our big C constant. Well, e to the 1/2 0 is just, 1/2 times 0 is just 0. 0 plus c is c. So we get 2 is equal to e to the c. E is well known, it's 2.718, etc. 2 is well known, it's 2. C is the only thing we don't know here, so let's solve for C. We're going to take the natural log of both sides to eliminate the exponential. Ln of e to the c is just c. So we know c is equal to ln 2. So that's the value of c that goes into our general solution. So that goes in right there. So our particular solution, I guess I'll write it over here. Our particular solution, well, it's the general solution, y equals e to the 1/2 x, but we know what big C is now. Big C is ln 2. So I'll put 1/2 x plus ln 2, and that is the solution to the differential equation, y prime is equal to y over 2, if we also know that y of 0 is equal to 2. All right, and so that's kind of what 9.3 is about, is seeing if you can use some algebra to separate these separate differential equations, use anti-differentiation, and then solve, if necessary, a particular solution, which means find the value of C for these examples. Let's do a couple more of these. Again, feel free to pause the video if you want to give it a try. If you kind of get the gist and want to see if you can do it on your own, that would be a great thing to try. So I'll do example B for those who have come back from pausing or people who want to see another example. So we have a differential equation here, y prime is equal to x over y squared. Once again, resist the temptation to write y prime all the time. It's really dy dx. This is the Leibniz notation, which is very preferable to the Newton notation. The prime notation is the Newton notation. The Newton notation just doesn't work for a lot of applications. The Leibniz notation works for everything. So defer to the dy dx, the Leibniz notation. It'll certainly make your life a lot easier when doing calculus. So I need to separate all my variables. This one ends up being pretty straightforward, just by getting rid of the two denominators. Multiply both sides by dx, multiply both sides by y squared. I'm going to anti-differentiate both sides. The antiderivative of y squared dy, right? Y squared dy, that's y to the third times 1/3, y to the third power times 1/3, or divided by 3, plus some constant, but I'll put the constant on the right-hand side. The antiderivative of x is x to the 2 with a 1/2 over here, and then we'll put my big C over here. And I need to solve for y. So I'm going to take this equation. I'm going to multiply everything by 3 to get rid of the 1/3. And I'll go up here. So 3 times 1/3, well, that's just 1, so I get y cubed. I get 3 times 1/2 x squared, which is 3/2 x squared. And I get 3 times c, which is 3c. But remember, c is a constant that we're going to just solve for anyway. So you can feel free to call this like even bigger c, like super c, right? Or you can call it k or something, right? It's just some constant. You can leave it as 3c if you want, if you're uncomfortable making it a big constant. But honestly, it's just a constant. So a constant times 3 is still just a constant. Now I'm going to cube root, or take the 1/3 exponent of both sides. That will undo the cube, right? The inverse of cubing is cube rooting, or 1/3 exponenting. Do the reciprocal exponent, the 1/3 exponent. Y cubed to the 1/3 is y, and then there's no way to simplify this creature, so I'll just write 3/2 x squared plus my super c to the 1/3 power. That's my general solution. All right, this is the general solution. And then I'm going to find a particular solution, because as a follow-up question, it says, give the particular solution if we know it passes the point 2, 1. So I just plug that information there. Y is 1, X is 2. C is C. And that's my big equation. Now I just need a bunch of algebra to solve for C, and then I can write my particular solution. So 3 halves times 2 squared, well, it's 3 halves times 4. So 3 halves times 4 is 6. So now I'll undo the 1/3 by cubing both sides. The third exponent to the cube is just exponent of 1. So what do I get here? What do I get here? I get 1 cubed, which is 1. C plus 6 to the 1/3 cubed is just 6 plus C. And then subtracting 6, I know C is -5. And so my particular solution would have C equals -5. So I write out my general solution, but then I put in the -5 in for C. There's your particular solution. All right, well, you got one more of these to try. If you haven't give it a go, haven't tried it and given it a go yet, this is a great opportunity. I have a slightly more complicated one here. So I really invite you to give it a try, just instead of like passively watching. Try it yourself. If you don't get very far, that's fine. At least you know where you got stuck and how far you got along, and you can see how to get unstuck. And that way you'll have confidence going into the homework that you've done a few of these and that you kind of understand the steps. So give it a try if you're willing. If not, that's fine. But I'm going to show my solution in a moment. All right, here we go. So we get 3 minus e to the y. So this is 3 e to the minus y equals x e to the minus y. And this y prime, as I've suggested before, right, is dy dx. So now this looks more complicated. We have to get all the x's on one side, all the y's on the other side. We have y's all over the place. We only have x's in one place, which is kind of nice. Oh no, we have x's in two places, x here and an x here. But there's x's and y's all over the place. So let's try to get like all like stuff on one side. Let's get all the dy dx stuff on one side and all the non-dy dx on the other side. So maybe I can write this as 3e to the negative y minus x e to the negative y equals negative dy dx. Or maybe you move the dy dx to the other side and made it a positive and made these other guys negative. It doesn't really matter, right? You could have done -3 e to the negative y plus x e to the negative y. It doesn't really matter. You just have to sort of get those separate a little bit. Now check this out. On the left-hand side, we have a common factor of e to the negative y. So this is called factoring. We can factor out e to the negative y. And what's left inside, well, if I factor e to the negative y or divide by e to the negative y, I'm left with a -3. And over here, I'm left with a plus x. And I haven't done anything to the right-hand side, so it's still dy dx. And lo and behold, I have two things being multiplied. One of them is just in terms of y. That's this guy over here. And the other one is just in terms of x. That's this parentheses things here. So I have an opportunity now to get all the x's on one side, all the y's on the other side. All right, so I'm going to put the dx over here, and I'm going to put e to the negative y over there. So I'm going to multiply both sides by dx. That way, the dx divided by dx is just 1. That's very nice. And then I'm going to divide both sides by e to the negative y. E to the negative y divided by e to the negative y is going to be 1. So these guys go away. And then I just get e to the y in the denominator and dy in the numerator. All right, so I have -3 plus x dx equals dy over e to the negative y. Okay, I'm going to anti-differentiate both sides. All right, once I separate the variables, then I anti-differentiate both sides so I can solve for y. All right, so the antiderivative on the left-hand side, that doesn't look very challenging because we know what the antiderivative of a constant is. And we know what the antiderivative of just x is. So these ones just use the normal power rule. On the other side, we have e to the negative y, which you can use the fact that there's a negative exponent and do the reciprocal. So this is just e to the positive y in the numerator. And that too is actually a straightforward integral to do. Integral e to the y is e to the y. All right, so let's finish up this problem. The antiderivative of -3 is -3x. Antiderivative of x is x squared times a half. And we get a plus c, which I'll write on the other side. Here we get e to the y plus some c. I can write the c on the other side. I can write the c anywhere I want. I'm going to write the c over here with the other x stuff because I'm trying to solve for y anyway. I'll write c. I can write c on either side. So I'm going to write it over here on the left-hand side, so it's just easier to solve for y. Otherwise, I just subtract c on both sides and it become a new super c or something like that. All right, separate the variables, anti-differentiate both sides, put a plus c on one of the sides, solve for y. We're solve for y by just eliminating the exponential here by doing the natural log on both the sides. And natural log of e to the y, that's just y. And we have our general solution. It's the very pretty natural log of -3x plus 1/2 x squared plus c. What a beautiful looking function. That is the solution to our differential equation, called the general solution to this differential equation we started with. And of course, we have a particular solution. So if you haven't got the particular solution, if you haven't had a chance to use if you hadn't had a chance to use the numbers to try to find the particular solution, it's a good time to try that. I'm going to plug in the numbers and try to solve for C right now to get the particular solution. Okay, so the x value is 4. So this is ln of -3 times 4 plus 1/2 times 4 squared plus our c, and that's equal to y, and y is 1 in this example. So what's all the math on the inside? We get -3 times 4 is -12, and we get 1/2 times 4 squared. 1/2 times 4 squared is 1/2 times 16, which is 8. So I get -12 plus 8 plus c equal to 1. And it looks like I need more space. So up here. So -12 plus 8 is -4. So I get ln of -4 plus c is equal to 1. I exponentiate both sides. That gives me, well, the e and the ln undo each other. They're inverse functions. So -4 plus c, e to the 1. This is an e. It looks like a c, but it should be an e. E to the 1. We exponentiate both sides. E to the 1 is just e. So I can solve for c by adding 4 to both sides. And now I know the value of my constant. So now I can write the particular solution. So the particular solution now becomes, well, the general solution was over here. So my particular solution, I'm going to write the y on the left-hand side just because, I like that. So the particular solution is y equals ln of -3x plus 1/2 x squared. Need a little more space. Sure. More space, please. There we go. So ln of -3x plus 1/2 x squared plus c, which we know is e plus 4. And that, my friends, is your particular solution to our general solution to the differential equation with the additional knowledge that it goes through the point of y4 is equal to 1. All right, so that's it for this video. Hopefully you found that helpful. Hopefully reach out to me if you have any questions or comments or any what-if scenarios, and I hope you have an enjoyable day.